Thank you everyone for joining us. It's series on evidence, models, and explanation. This is the 13th talk, I believe. We have 2 more remaining, but we are going out with a bang. We have a great series of talks lined up towards the end. So we're very pleased to have with us today Professor Wendy Parker. She's a professor at the University of Virginia. No, Virginia Tech or the University of Virginia? Yeah, Virginia Tech. Sorry. Yeah, Virginia Tech. Sorry for that. She works on a lot of different issues in the philosophy of science, but what is particularly interesting about her work is that she has focused a lot on the philosophy of climate science and meteorology, which is a burgeoning but still relatively underpopulated field in the philosophy of science, and one that certainly deserves a lot more attention than it currently has. So I think we're all going to learn a lot from the talk today, and I'm excited to hear from her. So without further ado, Professor Parker, would you go ahead?
Thanks very much, and thanks very much for having me. I agree with you that the area of study in philosophy of science focusing on weather and climate is still somewhat small but growing. And I noticed you have, I think I'm like the 3rd speaker in your series that's going to be doing something related with climate, which is, you know, for me really exciting, because when I started working on this like 20+ years ago, I didn't know anybody else who was doing it. So it's really great to see this development. So I'm going to be talking today about explanation, and in particular, the roles of simulation in explanation. It's a topic that's been of interest for me for a long time. And this talk is kind of bringing together several different threads of investigation that I've been looking at over the years. I hope you'll find something of interest in it. So if we're thinking about climate science, there are lots of different things we might like to explain, but some of the things that are of particular interest are changes in the climate system. So things like ice ages. This has long been a topic of interest to climate scientists. You know, what are things that could cause ice ages? What in fact has caused ice ages? Or more generally, what has caused large fluctuations in global temperature that we think have occurred historically? More recently, we're familiar with, you know, warming of Earth's climate system just in the last 100 years or so. And one of the targets of explanation that I want to talk about today is this period referred to as the hiatus. So it's this period that's shaded in gray here, where this global temperature curve, it's hard to see, but if you kind of block out the most recent warming, it kind of looks like things flattened off a bit there, and this became a target of explanation around 10 years or so ago. So I'll talk about that. But you can see the question that the scientists might be interested in answering is something like, you know, why did warming slow around 2000? And why has global temperature increased over the last century? What's the cause of this? So these are things that climate scientists want to explain. Why would it be hard to do that? Well, one reason is just that the system is a complex and complicated system, right? Many causal processes jointly shape the things that we think of as the main climate variables, like temperature or precipitation or winds, whether that's globally or in a region. So there's a lot of causes together that are acting. We do have some theory that is well developed for some of these processes, and I'll say a bit more about that in a minute. But for other processes, less so. That's another reason it can be challenging to explain what's happening. In addition, there's several what are often referred to as external forcing factors, things that can change climate conditions that are thought of as being in some sense outside the system. So things like changes in the sun's output and how much sun is coming into the climate system, volcanic emissions, and then human emissions of things like greenhouse gases. So these are all sort of external causal factors that can be sort of pushing and pulling on the system. And beyond that, you've got the fact that the climate system is going to vary in its conditions, even in the absence of things like changes in solar forcing. So climate scientists refer to this usually as internal variability, It's just capturing the idea that there can be kind of oscillations from year to year or even decade to decade in the system that aren't, in a sense, these changes aren't being driven by something external, but they're just representing the sort of unfolding of long-term processes in the system itself. So changes in, say, ocean circulation. So you have a lot of stuff going on in the system. You have limited and uncertain data, especially if you're interested in what's happening to climate variables before the 20th century, when the instrumental record is quite limited. And just to add further challenge, you can't do controlled experiments, right? You can't say, well, maybe it's this, so let's just do an experiment like a randomized controlled trial where we subject some Earths to this factor and some not, right? We don't have that option. So explanation can be hard here. And what I want to talk about today is how computer simulation is helping in the face of these challenges. And the idea is I kind of have two goals in this talk. One is to kind of share some features of current practice. So as a philosopher of science, I'm interested in, how do climate scientists, in fact, use climate models to make progress in their explanatory tasks? So one of the things I want to do is show you some examples of that. And then I want to step back, again, sort of wearing my philosopher's hat, and think a little bit about what we observe in those practices. So that's what I'm going to be doing. I'm going to start by just very briefly talking a little bit historically about some of the promise that the computer was seen to have when it came on the scene in the mid-20th century. And I'll talk about things like testing hypotheses, estimating contributions, and serving as surrogate observations. Then I'll turn to practice today, as I said, and I want to illustrate some important explanatory roles that simulations have in climate science. And I'll have two kind of case studies, and they're related to that second target of explanation that I showed you early on. So the late 20th century rise in global temperature, and then that early 20th century slowdown. So I want to look at how simulations are playing a role in explaining these phenomena. And then lastly, my further philosophical reflections, where I kind of reflect on the practice that I'm illustrating for you in the second part of the talk. Okay, so that's the plan. So first, the promise of the computer. I want to go back to the time before the computer and just say a little bit about what was happening in meteorology, which is closely related to climate science. So by the early 20th century, physicists had identified a set of hydrodynamic and thermodynamic equations that in principle might be used to forecast atmospheric conditions. So this paper by Wilhelm Bjerknes is a sort of landmark in the history of meteorology. And it's talking about, like, what are these equations that we need, and sort of understanding the prediction problem as one where what we need to do is identify the equations and then identify the initial conditions and get some solutions. The problem, right, was that getting the solutions is non-trivial. You end up with a set of differential equations, a set of partial differential equations, just focusing on this hydrodynamic and thermodynamic part of the atmosphere, and you can't solve these analytically. So what did people do? Well, before the computer, they had some graphical methods. So on maps, they had some methods that would be, in a way, a kind of approach to approximating some of the physical principles that were at work in the equations. And at least one person, Lewis Fry Richardson, tried to apply numerical methods by hand to try to estimate solutions to these differential equations. But it was hard, right? I mean, not a lot of progress was made, and you find commentators saying things like, theory is not particularly useful in this context. It's like we have the equations, but we can't do much with them. So the advent of the computer really brought new hope there. In fact, so the idea was maybe we could come up with some simplified versions of these equations that we might solve using those numerical methods, but with the help of a computer. So instead of it taking months to do a single forecast calculation, maybe it could be done before the weather actually unfolds. And this kind of hope has come to fruition, and even within within 5 years of the first successful numerical weather simulation in 1950, numerical weather prediction was operational. So from a prediction point of view, there was a lot of hope, and that hope, I think, has largely come to fruition. But even very early on, you find scientists, including those involved in the prediction challenge, like Jewel Charney, who you see here, who was instrumental in the development of those simplified equations used in weather prediction, you find them touting the importance of the computer and mathematical models implemented on computers for things other than prediction, and in particular for explanation and understanding. So here's a quote from Charney in 1955. He says, "The radical alteration that is now taking place in meteorology is due not merely to the ability of the machine, that is the computer, to solve known equations with known initial and boundary conditions, but even more to its ability to serve as an inductive device." So it's like, it's not just about helping us solve those equations that were previously intractable, it's something more than that, this ability to serve as an inductive device. And he goes on to say a little bit more about what he means by that. "The machine, by reducing the mathematical difficulties involved in carrying a physical argument to its logical conclusion, makes possible the making and testing of physical hypotheses." So this was one of the main benefits that he thought the computer could offer us as an inductive device. It could help us carry a physical argument to its logical conclusion, thereby allowing us to test physical hypotheses. And here we kind of circle back to those challenges that I mentioned at the outset, right? He says, in a field where controlled experiment is still visionary and physical model experiment difficult, he's referring there to sort of dishpan experiments where people would have a large pan of water and use that rotating as a way of probing certain hydrodynamical questions about the atmosphere. So the computer is sort of held out as, hey, this might allow us to make some progress in testing physical hypotheses. So this was in meteorology. You find the same kind of optimism from, in the climate context, from Ed Lorenz, another sort of luminary in the field, in one of my favorite papers of all time, this climatic change as a mathematical problem. He says, there appears to be in the computer simulation model a new and powerful tool for studying the phenomenon of climatic change. Perhaps there should be a center for climatic change hypothesis testing. Of course, today we do have lots of those centers. This was 1970. It has been said that new hypotheses are being introduced much more rapidly than older ones are being rejected. The next 10 years could see a reversal of this trend if the models are properly exploited. So again, Lorenz, and there's so many nuggets of insight in this paper, but the one that he's highlighting here is very similar to the one that Charney was highlighting, that somehow these computer implemented mathematical models provide us with opportunities for testing hypotheses in ways that we're otherwise not able to do. And in Lorenz's time, he was primarily concerned, well, he was concerned with lots of different hypotheses, but the ice ages were still sort of looming large on the landscape for climate scientists as what might be explained. So when he talks about new hypotheses being introduced, he often has in mind hypotheses for past ice ages. So I wanted to he gives an illustration of an example of the kind of benefit in testing that he thinks the computer can offer us. He says, such testing, such hypothesis testing seems essential if the hypotheses are not simply to remain hypotheses forever. For example, one might argue convincingly that a decrease in evaporation from the ocean would bring about a decrease in surface salinity or saltiness, which would inhibit vertical overturning in the ocean and thereby favor the formation of sea ice, which would in turn bring about increased reflection of solar radiation and thereby lower the atmospheric temperature. So he's saying you might tell yourself a causal story about how a change in one variable would be causally linked to changes in other variables, such that at the end of the chain of reasoning, you get, say, a climatic change of interest, in this case, a lowering of atmospheric temperature. But it's all qualitative, right? So he goes on to say, such reasoning could be completely sound and yet not be particularly relevant to the problem of climatic change if the decrease in temperature arising from a given decrease in evaporation should prove to be negligibly small, if the quantitative story doesn't pan out. or if the decreased evaporation should simultaneously initiate a second chain of events, which would favor a rise in temperature. So maybe you were sort of tracing this one causal pathway. You forgot that there's another side effect of, say, step 2, which would actually, initiate a second chain of events that might cancel out the cooling that you were foreseeing. Yet all the essential features of this reasoning can be incorporated into a mathematical model, and the step-by-step numerical integration of the equations will then constitute a system of bookkeeping for the ensuing temperature changes. So this is Lorenz kind of just in a toy kind of example, giving us a sketch of how, we might be able to tell ourselves plausible causal stories about climatic change, but the computer and computer models could serve as a kind of quantitative bookkeeper for us that helps us check their quantitative plausibility, not just their qualitative plausibility. So without, I could spend a lot longer just probing and exploring some of the other insights that Lorenz presents in that paper. But here I'm just going to summarize what I take to be some of the key potential contributions that people like Charney and Lorenz see the computer offering in its role as a kind of inductive device to help us explain and understand the atmosphere and climate system. So the first one we've seen explicitly, and that is testing the quantitative plausibility of explanatory hypotheses. So we might want to ask, according to theory, is this set of causal factors sufficient to produce the phenomenon? We can't answer that question just by looking at the theory, but we might test it by representing the factors in a model and checking whether the phenomenon of interest occurs in the simulation. So it's probing the quantitative plausibility of the hypotheses. More generally, we can use the computer, these kinds of models, to estimate quantitative contributions. So again, we might ask, according to theory, how much does this causal factor contribute to the outcome of interest in the real system? We can't answer that just with our minds thinking about it, but we might simulate the occurrence of the outcome, then rerun the simulation, allowing the causal factor that we're interested in to vary as it has in the system, while holding other potential contributors fixed. So again, a kind of numerical experiment that we might do. This is also talked about. And lastly, something that Lorenz touches upon as something that we might hope for in the future, which I think we've now reached this point, is using simulations as surrogate observations. He doesn't use those terms, but he talks about studying the simulations as a means of suggesting hypotheses. So we might ask, how are causal processes in the climate system together producing this phenomenon that we see? We know that it's happening, but we don't really understand how the processes we know to be acting could be making this particular kind of phenomenon. So here the idea would be, see what's happening in simulations where that phenomenon occurs in order to arrive at those hypotheses. So I think that these are kind of ways that people saw the computer and computer simulation models potentially helping with the explanatory tasks that climate scientists face in the sort of situation they found themselves in, where they had some development of theory, but they couldn't solve the equations, they couldn't foresee what the equations entailed on their own for complicated situations like those in the real system. Okay, so that's the history part. Let's talk a little bit about today's practice. And so kind of how are things panning out now? So in today's climate modeling kind of context, we have mathematical models that are just sort of pencil and paper models. We also have computer models that are very complex. They range from these very simple models, as I said, to very complex models that try to represent the ocean, the atmosphere, the land surface, the sea ice, try to represent a lot of different components of this climate system that you see represented here. The complex models, these are definitely computational models, right? They are ones that are run on computers, in fact, usually on supercomputers. They try to, sometimes people will say the climate system in a box, right? It's trying to capture as many of these processes that we see in this sort of schematic of the climate system in our computational model. Insofar as we can, this is done using physical theory. So those fluid dynamical equations, those thermodynamical equations, versions of those are in fact used in the model. as well as equations related to radiation transfer, or pick any of these processes and you can imagine some of the physics that would be relevant. Of course, some processes aren't well understood yet, and some of them are happening on scales that are so small that they can't be kind of explicitly simulated in the simulation, but they have to be accounted for in simplified or more idealized ways. These are parameterizations. But how do they work? Well, they then try to solve a set of equations representing these processes using numerical methods, either on a grid in the sort of picture you see here, a three-dimensional grid, or using spectral methods. So these are the sort of complex end of the spectrum models. They're trying to capture as much of this stuff as they can in the model itself. And so the thing I just want to emphasize, because sometimes people think that these models are just like statistical curve fits or something. These are process models. They're trying to represent physical, chemical, biological processes that are relevant. They are grounded in physics. So if you look inside, for instance, here's just a couple of screenshots from the description of one component of one climate model, the community atmosphere model at NCAR. It's 224 pages long, the description of the model. And you can see that what they're doing is trying to apply physical reasoning and theory to represent these processes that are relevant to the climate and the climate's evolution. Okay, so now let's look at a couple of case studies where we see today the use of the kinds of methods and the uses of computer that Charney and Lorenz were envisioning in the 50s and the 70s. So I'm going to start with a really simple example where we're going to use computers to help us test the quantitative plausibility of explanatory hypotheses. So here's a hypothesis that might look familiar or might be one that you've thought about before, right? That human-related factors like rising greenhouse gases and natural factors that we know to be operating, like the sun's input and volcanic eruptions, that these things are together sufficient to produce the kind of 20th century temperature changes that we've observed. Suppose we had that hypothesis, and we might tell a qualitative causal story about how rising greenhouse gases will contribute some warming, and volcanoes will, when they erupt, will contribute some cooling. But how can we get beyond the qualitative story? Well, we might run some simulations, right, that represent both these human and natural factors insofar as we understand them to be acting in the system. And we look and see, does it actually fit with the temperature changes that we've observed? So this is actually a somewhat old figure from the 2007 IPCC report, where you see observations in black, and then a whole bunch of simulations from climate models, complex climate models in yellow, and the red line is just the mean or the average of those simulations. And what you find is that, right, the red line is reasonably well tracking the black line. So in this case, does the observed, we check, does the observed level of warming occur? And the answer is yes. So this would be an example where we're checking the quantitative plausibility of a particular account of what's underlying this evolution of global temperature. We have a set of factors that we hypothesize to be sufficient. We try to represent them in the model, in our models, and we see if we can reproduce the temperature evolution. We can do it again for a hypothesis that says, well, maybe the natural factors alone would be sufficient. Maybe we don't need the greenhouse gases. Same thing, we run simulations, but this time we hold the greenhouse gas levels fixed, say at their pre-industrial levels, let the natural factors like solar changes unfold and see what happens. And in these simulations, which are in blue, we don't see them tracking the black line very well, at least in the second half of the 20th century. So here's a case where if we think of this simulation study as a kind of a check on the quantitative plausibility of the hypothesis, it doesn't pan out, right? The quantitative check says it doesn't look like we can account for things in this way. So even if we know that changes in solar forcing can sometimes have a warming effect, based on what we know about solar effects now, it doesn't look like they're sufficient to account for the observations. Going further, I said in more general terms, you can kind of use simulations to estimate quantitative contributions. And when we move beyond kind of simple just plots of global temperature like this. Some studies try to break things down further, try to estimate the quantitative contributions of the different factors that we think are relevant. So sometimes you'll see figures like this, where you can see different potential contributors: solar forcing, greenhouse gas forcing, ozone forcing, volcanic impacts, right? There's an estimate from the model of what these different factors are contributing toward changes in global temperature. And so this is a strategy that's also employed to estimate not just these sort of global temporal evolutions, but actually spatial patterns as well, and how spatial patterns evolve over time. These are often referred to as fingerprints of particular factors, where you hold other factors fixed. So this plot is one looking vertically through the atmosphere, looking for different potential sort of effects on climate, different forcing factors. So here we see greenhouse gases, here we see sulfate aerosols, volcanic aerosols, changes in the sun's irradiance. The idea is to run simulations where each one of these factors that you see is allowed to vary in accordance with how we think it has varied in reality, while holding the others fixed. So these are kind of signals associated with these different potential contributors. So we're using the simulations to estimate the sort of isolated causal contributions, what these would do if they were acting in isolation. And then in actual, attempts to account for climate change in the late 20th century, there's a much more formal procedure that's employed, where statistical tests are carried out that ask whether we can combine these fingerprints or spatiotemporal patterns, as well as what we know about internal variability or the year-to-year fluctuations that would occur even without forcing. We ask whether all those things together are quantitatively consistent with observations. So these are attribution studies. So these model simulated patterns play a crucial role in these kinds of studies, which are able to demonstrate a kind of rough quantitative consistency, not just with that evolution of global mean surface temperature, but with the evolution of spatial patterns over time in the system. And not just for surface temperature, but the one I'm showing you here, right, is vertical temperature profiles, other variables as well. If we look at what the most recent IPCC report says about attribution, where do they end up after doing studies like this? Here's one headline statement. It's extremely likely that more than half of the observed increase in global average surface temperature in the late 20th century was caused by the anthropogenic increase in greenhouse gas concentrations and other anthropogenic forcings together. Now, what does extremely likely mean? Well, the IPCC has a kind of calibrated language. Extremely likely isn't one of their standard terms, but if you look down at the bottom here, extremely likely means that they judge it to have at least 95% probability of being correct, right? So take the statement, more than half of the observed temperature increase is anthropogenic. They say, like, we would attach a sort of credence to that, or we would attach a confidence to that of at least 95%. So that's, they're confident about this. In fact, the central estimates of what greenhouse gases are contributing is larger than what's observed. So these are some estimates of of different contributions, and this black one is the observed temperature change over this period that they're examining. The estimated contribution from greenhouse gases, you can see here, is far exceeding, the central estimate far exceeds the observed warming. So the way it's understood is that what we're observing is greenhouse gas effects partly compensated for by aerosols, which have a cooling effect by reflecting sunlight. But what I think is important about this is that they are, in their conclusions, like, they are attempting to take account of uncertainties. They don't just report in a simplistic way, the central estimate of our models is X amount, and we believe that's how much warming has been contributed by human factors. No, they make a much more hedged and rougher statement that they're confident about about more than half of the warming coming from anthropogenic effects. Okay, for my second case study, I want to look at this episode referred to as the hiatus or sometimes as the pause. You might have trouble seeing it just by looking at the time series of temperature change here. But if I cover up the right-hand part of the graph and you imagine that you were living in this gray period here and you didn't know what was going to happen in the future, the question of interest was, why does the temperature evolution appear to be leveling off in this period here, right? So since then, the temperature has once again risen quite sharply, but at the time, there was a question about what was going on here. The question was, as I say, why did warming slow around the year 2000, or at least appear to slow? There were a number of possible factors, right? Maybe there were some changes in forcing. Maybe the sun was doing something different. Maybe we had a lot more small volcanoes that were emitting more cooling material than we had expected or had seen recently. Maybe this was a kind of natural fluctuation due to these kind of long-term oscillations and cycles related to the ocean. Or, and this was a genuinely pursued hypothesis, maybe it was partly a kind of observational error due to places where there are gaps in observations where we thought warming was probably happening more rapidly. And if we're missing out on some of those observations, we might not capture the full warming increase. So there were a lot of potential factors that people could readily point to as possible, contributors to a slowdown like the one observed. There was also a lot of pressure to give some explanation. So the sort of narrative around the hiatus and the slowdown started to be that, from the sort of, so-called skeptical commentators was, suggesting that the fact that temperature wasn't warming more indicated some serious problem with the whole idea of anthropogenic climate change, was somehow casting this into doubt. This was not something, I would say, that climate scientists thought themselves, that this was a cause for concern about, the basic ideas of anthropogenic climate change. But as time went on, it became an interesting scientific question that one might want to answer. And there was a kind of pressure to give some answer given these complaints that were coming from outside of the field. So a lot of effort was spent trying to figure out what was going on with the evolution of temperature in this period. Ordinarily, and that's why you noticed in the last example we just talked about, right, the thing that they were trying to explain was warming in this whole 50+ year period, not a small decadal period where we know things can vary quite a lot. Okay, so what I want to talk about, as I said, is how did the computer help with this challenge? How, when people wanted to explain, did the computer simulation models play an important role? And so here's a case where I think we can find an illustration of that using simulations as surrogate observations. And there are many other examples as well, especially in meteorology, but this is a nice climate one. So this was a study in 2011 by Meal et al., where what they did was they looked at climate simulations from models where greenhouse gases were going up at some moderate rate, so the system was being forced, but nevertheless, you found decades, 10-year periods, where temperature wasn't going up much, if at all, right? So you found sort of hiatuses in the simulations, and look and see what's happening. Look and see what was happening in those hiatus decades in the simulations. So they looked at 8 of these decades, and what they found was that if you look at the sort of geographical pattern of where temperatures tended to be a little warmer than usual or cooler than usual, these hiatus decades tended to have a pattern that climate scientists associate with what's called a La Nina situation, right? So one of these oscillations, we might have heard of ENSO or El Nino Southern Oscillation, right? It's a kind of oscillation that happens in the Pacific Ocean. One phase of it is called the El Nino phase. The other is the La Nina phase. And what they saw in the simulations was something that looked La Nina-like, this cool patch here in the tropical Pacific, which was also seen in some real-world hiatuses. So this is a pattern, this ENSO El Nino, La Nina kind of oscillation is usually thought at least to be partly, if not primarily a manifestation of internal variability in the system. It's kind of processes are unfolding in the ocean atmosphere. Even if it's not forced, you might observe this kind of oscillation. So what they further found was when they looked at what was happening in the simulations, they didn't just find this pattern, they also could see that in their simulations, more energy was going into the deeper ocean in the simulations in these hiatus decades. That's what you see in this lower figure. So in typical decades, you see heat going into the ocean. In fact, the vast majority of the heat that is being held into the climate system is going in the ocean. But in the hiatus decades, you see more of it is shifting to the deep ocean. So you might have a cooler surface ocean, but more heat in the lower ocean. So this was an interesting, thing to observe because we don't have very good observations of the deep ocean. It's not like we can just go check our, comprehensive deep ocean measurements and see if more heat is going into the oceans. But this kind of observation of what was happening in the models suggested and added a kind of basic credibility to a particular hypothesis about the hiatus, which was maybe the hiatus is due largely to internal variability associated with these ENSO La Nina-like oscillations, and warming is going deeper in the ocean rather than at the surface. So there's no puzzle about the system warming, it's not warming at the surface in the air temperature that we're observing. Okay, so this was a sort of important, interesting suggestion. Another use was in estimating quantitative contributions. So a really interesting study came out in 2013 by Kosaka and Shi, and I'll just read you some from the introduction or the opening of their paper. They say, 2 schools of thought exist regarding the cause of this hiatus in global warming. One suggests a slowdown due to changes in external forcing, like maybe changes in the sun, changes in volcanoes, while others considers the hiatus to be part of natural variability, especially influenced by a La Nina-like cooling in the tropical Pacific, what we were just talking about in the last slide. They go on to say, a quantitative method is necessary to evaluate the relative importance of these mechanisms. And what is their quantitative method? They say, here we used an advanced climate model. So this is a sort of, you couldn't get a much nicer explicit description of, here we're going to use a climate model to do this kind of probing of quantitative plausibility and probing of the relative importance of different contributions that we think could be acting. And so what they did, they did a very interesting kind of experiment. They required in their simulations that sea surface temperatures in the Eastern Tropical Pacific Ocean, so where that La Nina-like pattern is, they required that sea surface temperatures there track observations of the sea surface temperature. So they kind of forced the model in that region to track the observed temperatures. Now that's only 8% or so of the surface of the Earth. So it's a pretty small patch of the ocean that they're sort of forcing to take a particular set of values. But what they found was that their simulations, once they did that, the simulations tracked the observed evolution of global temperature during the hiatus remarkably well. So you can see this in this picture here. The area to focus on is this bit in the green circle. And what you find, so the black line is the observations. The purple line is what you might get if you weren't doing this experiment where you forced the little patch of ocean temperatures to track observations. And the red line is what they got in their simulations once they did do that intervention in the simulation, right? Once they said, we're going to force sea surface temperatures in this portion of the tropical Pacific Ocean to match observations of them and see what difference that makes. And it made a huge difference. Moreover, their simulations also reproduced some notable regional anomalies in climate. So there was a prolonged drought in the southwestern US, and you could see that in the simulations as well. So it seemed like a pretty exciting result. This is what they say in their paper, however. They say, the simulated global mean temperature is in excellent agreement with observations showing that the decadal cooling of the tropical Pacific causes the current hiatus. Our results show that the current hiatus is part of natural variability tied specifically to La Nina-like decadal cooling. And so this was, a high profile result. This was a commentary on it in Nature, where it was published, as many of these hiatus papers were published in leading journals like Science and Nature. But it seemed like a bit of a hasty conclusion, right? And this is what some climate scientists quickly pointed out, right? So this is Kevin Trenberth. This paper identifies a pattern which we agree is an important part of what's going on. What this paper does not do is analyze the role of changes in forcing. So they only kind of probed this one potential mechanism that they identified. They didn't investigate the other. Nor does it deal with where the energy is going, such as our work on the deep ocean, nor does it deal with why. So it's like they sort of calling them out for doing something interesting, but maybe going a little too far in assuming that they identified the single main cause of what was happening. This is a pitfall that I'm going to come back to at the end. And so what you see in this comment from Trenberth is like, look, there's a lot more that needs to be investigated, other things that we need to attempt to quantify and understand, not just, what we see in this particular study. And so my last example of using simulations to try to do this more comprehensive estimating of quantitative contributions is this study by Huber and Knutti in 2014. And they did another really interesting kind of experimental approach with their simulations. They identified these things called variability analogs. This is what they called them. And what they did was they, in order to try to understand the contribution of that La Nina-like pattern, what they did was they looked in simulations where there wasn't any forcing of the system. The system was just evolving with all the things that could force it held constant. So the way it bounces around then is meant to be a kind of simulation of internal variability. They looked at those simulations, very long simulations, and they tried to find 15-year segments where the evolution of this parameter that's a kind of measure of El Nino, La Nina behavior, where that index looked like the index that we saw for observations. So they looked for patterns of ENSO behavior that were similar to the ones we observed in the real climate system. And then they asked, well, in these simulations where we're getting ENSO behavior like we observed, what is happening temperature-wise? So it's kind of the opposite. It's different from what Emil et al. Did. So they asked, what was temperature doing when we find these kinds of ENSO analogs in our simulations? And they did find there was a cooling effect on average in these 15-year segments when we have ENSO-like behavior that is resembling observations. So this was their approach at sort of trying to estimate quantitatively this component, the ENSO internal variability component. They didn't stop there. They also tried to estimate the contributions of changes in solar forcing and volcanic aerosols by running intermediate complexity climate model. So instead of using the fanciest models, they use some intermediate complexity models. And to understand what we mean here by changes in solar forcing and volcanic aerosols. So when people made projections of what the global temperature would do, say from 2000 to 2015, those projections were based on assumptions about what the sun would do, how many volcanoes would erupt, and so how much aerosols would be released by various countries around the world. That was in advance, right? So in the period since then, now let's say it's 2013 and Huber and Knutti are investigating this, now they can actually say, well, what did the forcings actually do? What do we think the sun actually did in that period? How many volcanoes do we think actually were erupting? How much aerosol do we think was emitted actually by various countries? Let's update our forcing estimates and see how that affects the projected temperatures. And again, they found this was going to be contributing a cooling effect, which they could quantify, a cooling effect relative to what had occurred in the simulations where they were just kind of guessing in advance at what the sun and volcanoes would do. So putting it all together, if they adjust their original climate model projections, which we saw previously in some of the other figures, these light blue ones, part of the concern was that the light blue line seems far from this orange line at the bottom over this period between 2000 and 2015. If you take into account the adjustments that they estimated for internal variability, that is for having a La Nina-like pattern. You take into account the fact that forcings, the sun's behavior of volcanoes, weren't exactly what had been assumed when this original light blue line was made. And if you also take into account some of those concerns about coverage with observations, you end up with this dark blue line as our model estimate and this upper orange line as the observational estimate. And so things look much more similar. We sort of see why we wouldn't have expected as much warming in that period, and how the simulations from the models are actually not nearly so far off from the observations as it looked like at the start of the analysis. So it was a pretty good accomplishment, I would say, where a lot of different modeling efforts came together to give an account of this, particular 10-year, 15-year period in the temperature record. Okay, my last section then, so that section that I just finished was meant to give you some concrete illustrations, concrete case studies where we see climate scientists employing simulation models in explanatory practice in some of the ways that people like Charney and Lorenz were foreseeing and hoping for decades ago. Now I want to step back from that and just offer a few reflections wearing a little bit more my philosopher of science hat. And the first thing I want to point out about what we see in this practice is we see what I would call explaining with models, not what is sometimes called model explanation. So Elisa Vokulich, in fact, a co-author of mine, we're working together, so I'm sorry, Elisa, I'm going to disagree with you a little bit about something here. She, in a paper in 2011, offered an account of model explanation. So the puzzle is like, well, how do we make the case that scientific models explain, given that we know that they're idealized and simplified, and we expect our explanations to be often anyway kind of veridical or true or approximately true in some way. So she tries to offer us an account of how models can explain. But what and it's a very interesting discussion with lots of good insights, but the bit that I'm taking issue with as a sort of understanding of practice is that she and many other people who think about models and explanation often seem to envision a kind of appeal to a single model, where the question is, how could this particular mathematical model we have explain some phenomenon? And a story is given in terms of, for example, the structural similarity to the target system or something like that. But what we see in the kind of cases that I've been showing you is that explanations often draw on a mixture of results from several models. They're kind of pieced together, maybe even different types of models, as in that last study I told you about. And alongside what we can learn from observations, it involves a kind of piecing together of estimated contributions through various efforts. And even when we look at, say, those individual pieces or contributions, the support that we get for the say, estimated contribution often comes not just from a single model or modeling study, but from accumulated findings of a number of studies that take somewhat different approaches. How do we sort of get at the contribution of ENSO and La Nina-like patterns? Well, there's the Kosaka and Shi approach, and then there's the way that Huber and Canuti did it with variability analogs, right? So all these things together kind of help to lend credibility to the fact that this might be making a substantial contribution, the internal variability. So the efforts at explaining, I think, that are considered most satisfactory in this context very often involve, as I said, explaining with the help of models, not a simple model explanation. So there's not this kind of simple story to tell about how a model, gives us an explanation in virtue of, being able to answer counterfactual questions or something like that. The practices do involve things like probing counterfactual situations, but the explanatory practice is really richer, where we're kind of piecing together lots of bits of information, that some of which help to reinforce each other before we get to the point where we think, we've got a good explanation here. The second thing I want to point out is that what we get, for all my optimism and sort of cheerleading in a way for what simulations are doing for climate science, At the end of the day, what we get is a kind of rough quantitative explanation, not a precise explanation. And that's for all the reasons that I noted at the outset, all the reasons that make explanation here challenging. We do have limited observations of the past. We do have uncertainties about how to represent some climate system processes. We do have limited computational power, which means our models can only have a certain resolution. So we have to idealize and simplify in various ways. So the explanations that we get here, they're quantitative, but they're often rough or approximate rather than extremely precise. And if you look at the different studies associated with the case studies I showed you, but also with other sort of explanatory targets in climate science, you will find that these kind of quantitative contribution estimates, they'll vary somewhat from study to study, depending on which model you're using and which experimental protocol or which strategy you employed. And in part, that's because climate models aren't perfect instantiations of theory in the way that Lorenz's bookkeeping picture might suggest, right? The models are idealized. They're simplified in various ways. There are uncertainties about how best to represent these things, and the models represent different trade-offs in some of those choices. So it's not surprising that we have only rough quantitative explanation, but I think it's important to note this kind of well, as much as I really like Lorenz's bookkeeping picture, and I think there's something absolutely correct about it, it's a kind of rough approximate bookkeeping that we end up with. But what I want to emphasize is, despite these limitations, nevertheless, I think we see genuinely important progress being made that moves climate scientists beyond the kind of causal stories that Lorenz was talking about in the 70s, right? When we think about the case study involving explaining 20th century warming, we see quantitative conclusions, and we see them sort of, in a way, trying to take into account the uncertainties that are recognized to be present. So the uncertainties are there, but it doesn't mean that we can't have a quantitative conclusion. It just means it's a rough one. Remember, the conclusion was something like, it's extremely likely that more than half, right, of the warming was due to anthropogenic factors. And likewise, in the case of the hiatus, right, I think it's important progress to show that the hiatus is quantitatively explainable from the perspective of current theory. It doesn't present a challenge to basic understanding of anthropogenic warming, as skeptics contended. So at the end of the day, climate scientists can't say, well, we can tell you, to the third decimal point, how much of this should be attributed to internal variability versus fluctuations in solar output. But what they can show is that within the bounds of reasonable estimates for these different factors, what we're observing is perfectly explainable. It is not something that is stretching us or constituting an anomaly in a Kuhnian sense. And I think that's real progress. And the last thing I want to talk about is sort of where I think we do need to be careful. And we saw that already in one of my case studies. There are clearly a couple of pitfalls lurking here when we're using models for explanation. The first is this pitfall of sort of just hasty explanation, right? Too readily concluding that a particular explanation, often a simple one, that we find quantitatively plausible in light of our modeling results, right? We might too quickly conclude that that's the actual explanation of the phenomenon we're interested in. So it looks like the thing we focused on in our study could explain it, and we jump to the conclusion it must be what actually is the explanation. We want to avoid that. The other pitfall is what I would call entrenchment or explaining away, where we might, find a way to dismiss virtually any potential challenge to our preferred explanation or theory by focusing on advantageous model corrections or tuning of the model in ways that will facilitate support for our preferred explanation. So I think that this is another thing that we need to be on the lookout for. I think we can understand something about when the risk of these pitfalls is high. There are a bunch of factors together, I think, that come together in the climate context to make these real risks. One is that the things we're trying to explain often can have complex contingent causal histories. In other words, there's often a large causal menu of potential contributors to what we're trying to explain. If you look at discussions of, I thought I had a thing here. Yeah, when you look at discussions of kind of retrospective discussions of like the hiatus, you find authors sort of listing out all the different, potential explanations that people, or explanatory factors that people could bring out. There's a large menu of potential causes that we might appeal to when it's time to explain something, which, in sort of less charitable terms, you get portrayed as just excuses for what's happening. So part of the challenge is the risk becomes a little higher when we have this large causal menu, when we have serious uncertainties about the effects of these different, entries on the menu, when we don't have a lot of opportunities to now empirically test our potential explanations. And also, I think an exacerbating factor is when finding or keeping an explanation serves our values or interests. So in the climate case, you can think of that as like, the contrarians or the skeptics are saying X indicates that the entire climate science edifice is shaky or false. And then the climate scientist may feel the need to show that X can be explained. And then you get this sort of risk of, say, hasty explanation or explaining away. So I think that these risks are there, and I will say just in passing, they're not only here in the climate case, right? I think all of these are met, for instance, when models are used in explaining things like patterns of COVID prevalence. This is something I've been talking about recently with another speaker in this series, Eric Winsberg. We may want to write something on that. So despite these pitfalls, this is my last slide, I do remain optimistic. I think it's important to recognize these risks of pitfalls, but I think what we should take away from that is that we should look out for them and be on the lookout if we're climate scientists. But I think the case studies we saw today do provide some reassurance that climate scientists are, to some extent anyway, on the lookout for these pitfalls, because we see them doing things like attending to uncertainties associated with explanations that are informed by modeling results, not just taking them at face value. We saw this with the 20th century warming case study. We also find them calling out instances of hasty explanation. And finally, we find them acknowledging limitations. And here I would just recommend this paper that I show you on the right by Medhog et al. In 2017, which is kind of looking back over a huge body of work investigating the hiatus and kind of sorting through the different proposals, the different studies, trying to reach some conclusion about where we end up. And you find plenty of acknowledgements of the limitations of what has been learned and sort of humility in the conclusions reached. So I think there are signs for reasons to remain optimistic. And with that, I'll finish with just some references that you might want to check out if you're interested. Thanks. Oh, I can't hear you, Tarun.
Sorry about that. Yeah. Thanks a lot, Wendy. That was a really rich talk, and I'm sure that it has provoked a lot of thought and possibly some questions from our listeners. So I will now open up the floor to questions. If you have any questions, please raise your hand in Zoom. I'm sure most of you by now know how to do this, but in case you're not aware, you go to the participants window, which you can open up by going to the bottom of your screen or your Zoom screen. There should be a little button that says participants. The window should open up on the right-hand side of your screen, assuming you're on your computer. And there should be a little raise hand button there. So please use the raise hand button to indicate that you have a question you want to ask, and I will come to you. I would also request that if you have multiple questions, you ask one question at a time. If there are no further hands raised, you can raise your hand again, and I will come back to you for the second question if you have one. But please, at a time, please ask one question. Okay, with that said, let's get to the questions. Jyoti, go ahead with your question.
Hello, thanks for the wonderful talk. With the advent of computer and mathematical models, we have now advanced understanding of climate system and its science. Most importantly, it has helped us in prediction and develop two kinds of understanding, the two notions of understanding mentioned in the paper. So though we have now a lot of data about internal variability in a system, causal factors, and we are able to study the history of climate change and give explanation for it, are climate scientists ready to go beyond qualitative causal stories, meaning are we ready to intervene in the climate change process for our favor? It's more like man being able to control or tame nature, since we have so much of information now, and also we can like test a hypothesis using intervening simulation in a computer, or are there some formidable challenge to it?
Thanks. That's a great question. I would say that there are formidable challenges yet. I don't think we're ready for interventions. I mean, I think it depends on the intervention, but if you're thinking about something like climate engineering or something like that, where instead of trying to reduce greenhouse gas emissions, we think about, you know, mirrors in space or seeding the ocean or doing something like that. I think sort of massive interventions on the system, I think, are ones that we still want to be cautious about, even if we want to, even if we might be interested in studying them. So I think it's one thing to say we've made progress and can give something beyond qualitative stories when it comes to, you know, what's happening in the past. It's another thing to say we're confident enough in projecting what will happen in the future that we are ready to take on significant interventions to the system. And I think there's a need to be much more cautious about that.
Sure, thank you.
Okay, thanks, Jyoti. Don, you have a question?
Yeah, my question is about this idea of explaining with models. So I was reading your Erketnes paper, which came out earlier this year, evidence and knowledge from computer simulations. And there is an example of Sarah, who is explaining a surprising feature of objects in the Kuiper belt. And then you go on to give, do a wonderful job of showing how that constitutes higher order evidence, which the simulation is giving her to know, although in a psychological sense. So I was thinking, see, if the question is what explains these features of the climate, then obviously the answer is, well, it's something out there in the world. And so then the question is, well, if you're using computer simulations, then it appears as if, well, the simulation is giving you some evidence to tell me that there is certain hypothesis out there, which is the explanans for the explanandum that you have sort of identified. So in a way, I mean, all these examples that you've given in your talk, basically, they are just giving us evidence for choosing certain hypotheses over the other. Am I right in thinking in that way?
I think that's fair. I mean, it's, we're not going to get something for free. There's going to be this inferential work that has to happen. The way I think about it is, it is a testing of hypotheses, but in a different way from what we often mean when we think of testing hypotheses. So often when we think about testing hypotheses, we think you make a prediction, you go out and observe the feature of the world that you think is, the one referenced in your prediction, and you see, does the prediction match well enough to do the observations match well enough to your prediction? This is the kind of testing that's happening here. It's more like a quantitative consistency check, right? It's like saying, I've got a body of knowledge. I have some sort of reason for thinking that some causal factors that I'm aware of may be sufficient to account for what I'm observing. And then what I get from the simulation is either reinforcement of that in quantitative terms or reason to doubt it in quantitative terms, right? So I say, here I'm going to implement my knowledge in a much more refined way, and I'm going to ask quantitatively, do things pan out in the way that I'm expecting? But I agree, at the end, what you're getting is like, so suppose the simulation shows that the set of causal factors you've hypothesized is in fact sufficient to produce the phenomenon. Well, maybe you want to say, if you're thinking about where you're distributing your probabilities as a sort of Bayesian, maybe you're going to move some of your your probability over there, but you're not getting that information by going out and collecting new data, new observations. You are more probing your own knowledge system in a way that can be informative to your position. So I think that's how I would put it. Does that make sense?
Okay, yeah, thanks.
All right, thank you, Don. Mike, you have a question?
Thanks for the talk. This is so cool. I was wondering about the roughness of the quantitative explanations. And I was thinking about, you sort of focused on idealizations, simplifications, and uncertainties for obvious reasons. These are all really important. And something I was thinking about also was cases where not just climate science modelers, but modelers of all kinds often introduce de-idealizations and complexifications and certainties where there shouldn't be certainties, because they have to in order to get the model to, get off the ground. I was wondering if you thought of this as a different sort of roughness, a conflicting kind of roughness, or kind of just sort of more of the same sort of roughness.
Good. So I think what I'd say about that is that good epistemic practice would call for people to then introduce the roughness themselves when it comes to reaching their conclusions. So it might not be that the modeling studies are reflecting that roughness, so we're not maybe trying out different ways of representing something that we're uncertain about how to represent. But if we know that we've sort of artificially precisified something in the model, then when it comes time to reach our conclusion, we should take that into account. And I mean, one way, it's not exactly the same by any means, but a somewhat similar thing that you see is what I was talking about in the case of the IPCC conclusion, where they actually look at a bunch of different modeling results. They make some assumptions to get an estimate of how much of the warming is sort of explainable by human factors given our range of estimates so far. And then they kind of downgrade their confidence a little bit, even though they were still extremely likely. They downgraded a little bit to sort of acknowledge that the studies they're looking at aren't completely sampling the uncertainties that they recognize to be present. So I think that kind of secondary, more expert judgment step, that I think it's a really important part of good epistemic practice in here. It's not something to be criticized, it's something to be praised. But it can help deal with cases like what you're describing, I think.
Thanks.
Thanks a lot, Mike. Prashanta? Prashanta, you're muted. Yeah.
Can you hear me now?
Yes. Go ahead.
Hi, Professor Parker. Thank you for a nice talk. I have a general question. It's about the contribution of the climate science or in general, the paper you did on literature of explanation. So I will tell you what I see, and please correct me where I am confused, mistaken, and maybe I'll add something. So in the standard or maybe last 50, 60 years of literature on explanation, what we see is that most of the examples we use, they're very much a finished theories for Newtonian theory, Einsteinian theory, finished in a very standard sense. But here we see an emerging science which has a different perspective to give. That means, it is evolving. We are learning a lot of stuff. So it adds something new to the explanation literature. But also there is this, as you mentioned, it's not the one model or one theory, it's a set of models or some other things that contributes to explanation. And not just a one model, as we see light bends, Einsteinian theory and some auxiliaries. So, but there are also, you have some comments about an uncertainty, which are understandable, but you do use the word causal explanation. But how much is the causal stuff going on? So my broad question is that how and which way this climate science literature, and especially the talk you gave, shed lights on a different way on the current literature and explanation.
Thanks. Yeah. In some ways, I think it's very much in line with things we think about explanation. So as you point out, like I'm talking about causal explanation here, and I'm talking about that mainly because my interpretation of the literature when I look at it is that most of the time this is what climate scientists are looking for. They're looking to give causal accounts of what's happening in the system. So in that sense, it's of a piece with, you know, a main paradigm in explanation. Interestingly, you even find discussions from people like Lorenz, for instance, about something that we might associate with the deductive nomological model of explanation, because you might think, well, you might talk about explaining something in a certain sense just in virtue of simulating it, right? You've sort of shown that it follows in a rough way from your set of assumptions, your laws plus initial conditions. But that way of thinking about explanation is often characterized as a kind of inferior, you know, mode of explanation in this context, because of this idea of understanding, that you might feel like, okay, well, maybe I have successfully derived the phenomenon, but I still don't know, I still can't tell you in a sort of causal way why it happened. So there's that. But I do think that, yeah, I take one of the contributions to be just recognizing the richness of strategies that are used with simulation. So it's not just a matter of, you know, my first example where you run a simulation, then you leave out a factor, and okay, there's something right about that. That's a way simulations are used. But especially in the HIATUS case study, you see such a richer set of approaches to using the simulations with the variability analogs and so on. So part of what I wanted to do was, yeah, add some of this richness of practice. And secondly, exactly what you said, kind of push back a little bit against a tendency that I think we philosophers sometimes have to focus on simple examples where it does seem like a single model in a fairly neat and tidy way that we can talk about is doing some explanatory work, and it's pretty much the whole story of what we're calling an explanation in a particular example. And that does happen sometimes, but I think a lot of times it also happens in this much messier, you know, extended way with a whole bunch of models and modeling results being brought together in a piecemeal fashion to tell a story that one finds more compelling. So I want to add that to a sort of understanding of scientific practice, I guess.
Thank you.
So nothing wrong in what you said.
I see. Okay, thank you.
Thanks, Prashanta. Shinod? You're muted, Shinod. Yeah, go ahead.
Thank you so much. It was an exciting presentation. Part of my worry has been already expressed by Professor Prashanta. Anyway, I will go ahead with that. You are one of the philosophers from the beginning arguing for a comparison between computer simulation and experiments. Your 2008 paper where you kind of compared the strategies between Franklin's strategies of epistemology of experiments, and you kind of observe that, okay, we have similar kind of strategies in the case of computer simulation too. So I can see that kind of continuity even in the paper circulated for this talk, where we have terms like testing using computer simulation, then computer simulation standing in surrogate observation tool. Part of it I understand is how computer simulation practice become a self-legitimized tool in the repertoire of scientists. So what worries me is that, so take this example of computer simulation acting as surrogate observations. So usually with an experiment, there is a possibility for an alternate explanation from a better theory. In the case of experimental observation, so we have such examples from the history of science. But when computer simulations are used as surrogate observations, and how much can we explain this particular observed data using the simulation, because with some better theoretical apparatus, yes, particularly when our surrogate observations are a product of sometimes a mix of different models. You have also explained this in one of your earlier papers, I think 2009 paper, where you argued against a kind of an idea regarding the materiality aspect of simulation. So you can see the trend following here, but I would like to know a bit more about this theory dominant with the kinds of practice dominant approaches to this simulation. Thanks a lot.
Okay, thanks. I think you might have been cutting out just a little bit, so I'm going to do my best to answer the question. And if I missed what you were asking, please please clarify and point me in the right direction. I don't mean to be suggesting here, and maybe my answer to one of the earlier questions can help to reinforce this, but I don't mean to be suggesting that what we're getting from simulation here is like a perfect replacement for, you know, if we were able to do experiments on twin Earth, if we had a twin Earth, that I would prefer that, right? But I think what I'm trying to do here is to show how we can use these tools to make genuine progress in arriving at explanations, even if it's, and some of the practices that we engage in look like traditional, you know, we do use these terms, numerical experiment. I talked about surrogate observation. Some of the talk is reminiscent of more traditional modes of empirical investigation, not, you know, sort of theoretical investigation. But what I want to say is that I think this set of tools allows us to make genuine progress in developing our explanations, even if it's not, even if I wouldn't want to say it's exactly the same as doing an experiment on a twin Earth. And, you know, something I didn't emphasize, but that's implicit in the talk about hasty explanation, for instance, is just recognizing that, you know, suppose I get a simulation that does manage to reproduce the phenomenon I observed. I mean, it certainly doesn't follow directly from that I have identified the causal factors that are in fact the cause, right? I mean, I might say now I can take this to be a little more plausible, or I've enhanced the plausibility of this by showing that it wasn't just my qualitative thinking that suggested this might work, but kind of quantitative check of what my theory implies suggests that it might work. But, you know, there's still the question of what actually happened, what actually caused things. And this is something that's really nice at the end of that Lorenz paper. He says something like, something along similar lines, and says, you know, at the end of the day, we will still have when it comes to what actually caused past climatic changes, we will still have, you know, the pleasure of arguing, or something like that. You know, like, you know, we can use the simulations to get us to maybe rule out some things as not plausible, even though qualitative we thought they might be, and to show that others maybe look like they give us a very nice fit to the observations, and maybe that lends something to their credibility. But, you know, at the end of the day, we're sort of probing the quantitative plausibility of things. Not, it's going to take more work to say now we have arrived at what actually happened. And I think in the climate, you know, explaining 20th century warming, I think, you know, there's a case to be made for saying that, you know, we do have how actually explanations there, but it doesn't come just from simulations having given us these results. It also comes from our having background knowledge that says, you know, there isn't some additional causal factor that we've overlooked that could in fact be doing a lot of the causal work here, right? You need that additional assumption in order to move from, you know, we've got this quantitatively consistent story to the conclusion that we think we've got something like the actual story. Yeah.
Thanks, Vinod. Wendy, I should have asked you to do this earlier, but could you unshare your screen?
Sure.
Yeah. Yeah, great. Thanks a lot. And also, I have a question. So, I guess, so there's a kind of maybe like old-fashioned epistemology associated with explanation, where that seems to require a kind of epistemic transparency to explanations. So, I mean, the kind of analogy I'm thinking of is, I think when like computers first started doing mathematical proofs, there were a lot of mathematicians who were dissatisfied with a computer proof of a mathematical theorem or something like this, right? That there's something epistemically inaccessible about that proof that makes it not a proof in the kind of full-blooded sense. And so I'm wondering whether one might argue that something similar could be said of the kind of explanations that you're talking about, that what you have here is, so I mean, maybe this goes along with what you were talking about, Rich, about the analogy between explaining with models and explaining with experiments. In some sense, experiments might give you certain kinds of explanations, but some people might argue they're not kind of full-blooded explanations. What they give you are interesting new sets of explananda, which rule out maybe some potential explanations. And then, I mean, so two-state experiment in some sense ruled out certain ways of thinking about the world, but it wasn't really an explanation. You needed kind of quantum theory to explain what it was, because it, like, you have an inferential route to arriving at that, which you can kind of process cognitively. Now, I think maybe computer models are kind of a tricky thing here, because on the one hand, it's not exactly like an experiment, because you can say that, look, it's not an exact, because we have set up the underlying world. So in some sense, at the fundamental level, we know how this world works. And we know how the inferences work as well, because we set up the computational system. It's just that the inferences are really complex, and so we wouldn't be able to do them ourselves. But and I think this is the argument people make in the case of computer proofs in mathematics. But I'm wondering if you're kind of sympathetic to that line of thinking, that there is maybe a kind of sense of first-rate scientific explanation, according to which explaining with models wouldn't really count, where you'd really have to have kind of a theory accounting for why, say, this kind of ENSO oscillation leads to cooling, rather than simply the phenomenon, observing the phenomenon in your models.
Yeah, I mean, I think, again, if I'm not hitting what you're actually asking, just let me know. But I think that this is exactly what is often the position in climate science, that we don't just want to have simulations that reproduce the phenomena. That is unsatisfying. We want to be able to actually give accounts using our theoretical knowledge of what is happening. And the computer model is a kind of distillation of that theoretical knowledge, even if only approximate. But what's crucial, and this is again something I didn't talk about, but some other people have commented on, and is certainly, I think, correct, that visualization tools in this context are extremely important. So it's not enough to just, by analogy with the computer proof, it's not enough to just, generate results that numerically are, if you paired them side by side with observational data, would exhibit a certain kind of similarity. It's actually trying to understand, why is it that the simulation produced that result? Why is it that when Kosaka and she intervene on parts of the Pacific Ocean, does the global temperature respond in the way it does? I take kind of, in a way, the whole kind of program of using simulations in this context is geared ultimately toward that kind of causal understanding. And so it's just that we have to give that account kind of, as observers of the simulations, and as people who are probing the data in the simulation, the data the simulation generates, in the way that we probe experimental data, in order to, reconstruct for ourselves that causal account, right? So we may have the general qualitative causal story, then maybe we run a simulation and we get something that quantitatively, at least roughly, checks out. We're still going to want to look inside those simulation results and see, what was the jet stream doing? What was happening in the ocean? What kinds of weather systems were forming? How do we really understand how it came about in the simulation? And does that track with what our theoretical knowledge leads us to expect? So I feel there is the sort of dissatisfaction with computer proofs has an analog in climate science, which was what I was saying about the DN explanation kind of picture, where you could say, in a sense, we explain when we develop a simulation that produces in the simulation a phenomenon. But commentators like Lorenz would say, I'm no better off when I see that than if I just look at a real hurricane. I need to be able to see what's actually happening. in the processes inside the hurricane. And that's where the simulation via visualization tools can really help. So that would be my take.
Okay, thanks. Thanks a lot. Darshi, you have a question?
Yeah, can you hear me? Okay, thanks, Wendy. I do have a sort of general comment. Philos, you have a question?
No, I think he just accidentally unmuted.
Okay. Because if he has, I'll let him go first. Okay, so yeah, I have a kind of a general comment, but before that, if you don't mind, I would start with some humor. You know, in the early 70s, I was appropriately an Indian in Virginia, and before you were born probably, and during a basketball game, this is at William and Mary, you know, the people were carrying signs saying culture versus agriculture. That's when we were playing Virginia Tech. Hokies, right? Okay. Anyway.
We're playing today in football against Pittsburgh, which is where I got my PhD, so I have to be a little conflicted.
Panthers, right? Pittsburgh is Panthers, right? Okay. And I think your college is called Huskies, if I'm not mistaken.
Oh, from when I was an undergraduate, yes. Wow, that's good.
Okay.
Impressive knowledge.
Okay. So my teacher said doing philosophy is doing detective work, so I've done that. Okay. So I have this general question, and now you know that I'm a fossil, and my questions here are usually fossil questions. So when you start talking about explanations, I went to my hero and kind of a Bible of philosophy of science. It's Ernest Nagel's Structure of Science, and I just started reviewing the different types of explanations and his examples. So I think, like, models weren't quite around at that time, or they weren't big. But I think he would very much want to say that we do have models are explanatory and would probably fit somewhere the type of explanation we're talking about, somewhere in between deductive and probabilistic explanation, right? And so I agree with you that I don't see a difference whether, I think it's maybe some crude adherence to realism, right? That will say, okay, simulation models aren't real, right? But if we sort of infuse a little bit of structural realism or something, I don't see any difference between a mathematical modeling, whether it is a simulation model or whether it is a more real modeling. And in certain cases, like in COVID, I mean, I kept up with it a little bit. All we have available are simulation models, right? And so there, I can look at them and I can compare them in their explanatory powers just intuitively as a layman. I can say that, okay, Leverett has a little more explanatory power than does the Imperial College one or the Oxford College one. So I can do all of this. So I think explanation is, so I don't understand the objections that they are not explanatory as. So this is my general comment.
Yeah, well, I guess there's a couple of ways of thinking about why you might think they're not explanatory. And one way of, and I'm not advocating these views, I'm just presenting them, but I mean, one way is to say, you need a completely veridical account that an explanation is sort of must be true. And if the things that you're appealing to in order to, develop your explanation, and the thing that you sort of point to as justifying the causal story that you're telling, say, is clearly simplified, idealized, involves fictional elements, whatever it may be, then you could see how you could have a kind of prima facie puzzle there. Like the response is to say, well, we don't have to be so demanding about veridicality and explanation, but there's still a question about, how far is too far? Like, when does it get to be?
Exactly.
It seems silly to say we're explaining why this in fact happened when the things we're we're referencing are nothing like the things that in fact exist, right? So even if they're in the right structural arrangement, we might not want to say we've successfully we've successfully explained. So there's one way to push back focuses on this kind of truth element of explanation. And another way I think pushes on has come up a little bit already about kind of, well, look, ultimately you're just kind of working out the consequences of sets of assumptions that you've built into a representation. And that's just inherently different somehow from, you know, going out in the world and interacting with the thing that you're trying to give an account of. And I think, like, on some level, despite the fact that I've written these papers kind of undermining some of the differences between simulation and experiment, I think there's something right about that in the sense that, you know, the way I've been trying to tell the story here today is that the explanatory work that we're getting out of simulation, the kind of testing that we're doing is a different kind of testing. It's a testing of quantitative consistency. It's a test on the theory side in a way that says, are we correct that, you know, our body of knowledge has these kinds of implications that we think will match observations? That's what we're probing. That can still be really valuable in one's explanatory practice, but it is a bit different from some other modes of inquiry. But at the end of the day, I would still say, look, an explanation, and this is my position on it, but you know, I have this sort of, I would take a more epistemic view of explanation, that explanations are things we construct, they're not out in the world, bits of the world are not the explanations. Explanations are accounts that we give in light of what we learn about the world. And in that sense, you know, simulations can play a good role alongside lots of other sources of information that we have, so.
Okay, thank you.
Thanks, Dashi. Don, you have another question?
Yeah, just a small question. Have you come across any case studies in the climate science research which sort of exemplifies inference to the best explanation? How does one go about doing inference to the best explanation using climate models, especially computational models? Yeah.
Good. I do think, in fact, I'm trying to write a chapter right now for a short book, and the chapter that I'm working on is on explanation of recent climate change. So the kind of first case study that I was presenting to you. And I think that it's quite reasonable to understand what is going on in, say, explaining late 20th century global warming as a kind of inference to the best explanation, where we have a set of candidate explanations. We kind of show that some of them can't do the job, and we do that with the help of simulations in the way that I was showing today, like, for instance, that solar factors alone can't account for the rise in temperature that we observed. We use these kind of quantitative estimates as part of making our inference to the best explanation, but I think it happens alongside a kind of consilience between, you know, so it's not just that I'm able to, you know, estimate these quantitative contributions and show that they are quantitatively consistent with observations of, say, global temperature. It's the fact that I can also give accounts of, say, vertical temperature change and sea level rise and lots of other observations in the system that are sort of consilient with the explanation that I've chosen. And I don't know if that comes out as the sort of loveliness in Lipton's account, or exactly what which features of the, you know, of the best explanation. But there's something about the quality of the explanation that one is arriving at here that I think actually does help to align it with some ways of thinking about inference to the best explanation. So I think you're onto something there, and I think this case study does it, and I'm going to try to make a case for that in this chapter that I'm working on.
Oh, looking forward to it. Thank you.
Thanks, Don. So I have one more question that I'd like to ask. This is, so I was thinking back to some of the examples, the case studies you gave, for example, that simple comparison you had in the beginning between the kind of hypothesis testing case where you look at what happens when you have, I guess, anthropogenic forcing and when you don't have an anthropogenic forcing, and seeing that, you know, and at least a simple reading of that would just be that, okay, here we have hypothesis testing because we have this process model, and the process model kind of tells us what would happen in these two different cases. But really, at least based on the diagram you presented, the way you described it, it's not really one process model, right? It's a bunch of different models, and we're somehow aggregating them. And in fact, there seem to be quite a range of predictions that those different models gave us. And so if you were kind of reconstructing this explanation into an argument, I'm assuming the kind of controversial premises in those arguments would be statistical premises about how to aggregate these models, about, is it legitimate to treat this as to think that, taking the mean is in some sense a good estimate of what would really happen, or something like this, right? So there seems to be an addition when one goes into that domain where you're looking at aggregating models. There seems to be an additional challenge in translating that into an explanation, where it's not simply the kind of DN explanation that you talked about, but it's just being covered by the laws, because a crucial step in the argument is going to be the statistical assumption, which I imagine is quite open to criticism.
Good. Yeah, no, that's right. There's definitely debates about aggregation, less so, I would say, in the explanatory side when it comes to things like explaining recent warming, but more in the projection of future conditions, like how do we understand the population of projections that we're generating. There are different paradigms, different proposals statistically for how to deal with those. When it comes to the past, though, I actually think that one way of getting around it is by not, so all of the models together are important to telling the explanatory story, but that's different from saying when we're coming down to making our argument, one of our steps is going to be something like taking the mean and appealing to the mean, or any other even statistical feature of the distribution as important. It could be that we say something like, and I probably would advocate this, is, we look at, say, the range of results that we get, not so much worrying about them as a statistical sample of something or other, but just, no matter which of these you pick, you can reach this conclusion. So a kind of robustness in a way. It won't work for every explanatory task, but I think that's part of what you see when you get conclusions like that, more than half of the warming can be attributed. There is an assumption there that is made about treating the estimates that we get from the models as a kind of sample, and if you sort of do try to fit, say, a normal distribution and try to make that kind of inference, what you find is that you're very safe if you, so it's like this conservative move, right? Of like, you stay safe by not depending so much on the details of that aggregation procedure, but your conclusion is really more coming out of the range that you got, along with some statistical assumptions, but you kind of build in a kind of margin of error to a sort of, what's the word I'm looking for? Like a factor of safety or something, right? You kind of, you take into account that you don't think you've got the perfect statistical model when it comes to aggregating these things. So I don't disagree with you that there could be some very controversial assumptions if one tried to rely too heavily in the explanation on a particular statistical kind of aggregation procedure. But if you do it in a relatively simple way, and then say, moreover, I'm going to build in a kind of margin of safety, then you kind of shield yourself by weakening your conclusion a little bit. Yeah, what you're claiming to explain, how much you're claiming to explain.
Okay, thanks. Yeah. Darshi, you have another question?
Yeah, just a follow up on what Don said. I'm glad that's what I was thinking of actually. So if the inference to the best explanation. So I'm saying that in a case, I go back to the COVID case where the only thing we have available are mathematical models, right? Mathematical simulation models. And it doesn't matter to me, which comes out more accurate in terms of predictions, right? But in terms of inference to the best, I would qualify it and call the inference to the best mathematical model, okay, or mathematical explanation. I'll qualify explanation by saying model explanation. So I could still decide which one is the best, mathematical model there, using and looking at the entire model and what deficiencies there might be and all of that. So I can still decide, okay, this is the best, by making my inference to the best mathematical explanation, that this is the best model. And then later, whether prediction is accurate or not would not affect that assessment. And so I still go back, this adherence to crude realism is fine, but when in cases where you have only this to go by, then I think I don't see any problem in saying that the models are explanatory.
I guess I would want to maybe resist just a little bit and think about, I mean, just firstly by saying, I think even in the COVID case, we do have more than just mathematical models, right? We have, especially as I think, like, in March, maybe we might have had that, but we have now.
Yeah. That's what I meant. I meant in March, sorry.
Okay. People attempting to look at, say, how things have unfolded in different places, given different behavioral choices and so on. Now, those are still tricky to infer from, but there's at least some information now that is accumulating based, on what has happened in the world. And the second question I would have is just, when you say you would be trying to identify which of them was best, you mean in terms of like looking to see which of them had assumptions that seemed most reasonable to you, or what is the best in what regard and for what would be my, just to understand what you're claiming.
I mean, as a layman, I haven't looked at them carefully, but I think if I do look at them carefully, which is internally more consistent and mathematically, and it doesn't have any assumptions which which are kind of not verified or something like that.
Okay, yeah, I see what you mean now. Thanks.
I mean, this was a debate between Levitt and Carpenter, Ferguson. I mean, I don't know if you follow that. I follow that. Okay.
Okay, thanks, Dashi. Are there any other questions that people would like to ask? Okay, since there's no other questions, I just had a couple of like brief kind of maybe clarificatory questions about some of the case studies. These might be a little bit naive. So they're very, very basic questions. So I might just be misunderstanding what's going on. But also, I'm trying to remember exactly what the case studies were. So I think one of them, so this one of the papers you talked about, what they did was they kind of forced the surface temperatures to be what you actually observed. Is that? And then they showed that you got something like the pause. Is that right?
And showed that you got that the global temperature evolved similar to what was observed, given this intervention on the system. Yeah. Yeah.
Now, from the perspective of a kind of interventionist account of explanation, this seems like a very strange kind of intervention, right? Because I mean, again, I don't know much about how what the causal model of the system would look like, but I imagine that global temperature is not simply downstream of ocean surface temperature in the causal model, right? It's not simply like you can fix this and now you have global temperature as an effect variable. Global average temperature, presumably, I mean, I don't even know how to think of it. It's like causally influenced. Yeah, right. Yeah, and now I would imagine that I mean, insofar as you want to think of it as a variable in your model, I would think that variable in your model would also then have an effect on things like ocean surface temperature and so on. It's not, it's so, I mean, just trying to, if you look at it just as a basic interventionist thing where you constructed a causal model and then fixed this thing, it's unclear that, you have that kind of structure for this formal explanation. I guess that was one confusion I had about.
No, it's okay. I actually am not sure that I fully understand the experiment yet. I would need to go back and look again at the details. But what I can say is that the global surface temperature is not a variable in the model. So that's part of it. Like it's an aggregate of all the temperatures, right, around so, you know, take the temperature at all the grid points around the globe and average them. So it's more like an aggregate emergent property. So there's not like an arrow in a causal model that goes from a variable, you know, that is the global temperature, not in this kind of model. And secondly, but I think there is an interesting question that I still haven't resolved for myself, which is about the sort of physicality of what you're doing. And I think, you know, you kind of imagine if you're forcing temperatures, like how much intervention and forcing really needed to happen over time, you know, in that region, as opposed to, say, getting things roughly set up as observed at the beginning. And, you know, maybe it was just a matter of nudging them, you know, a little bit in the direction to maintain things, tracking observations. But I think there is a question about how do we think about this from a like physical consistency point of view? What kind of experiment is that? And I think that's really interesting, and it's just something that I haven't probed myself yet in detail. But I think we can sidestep the sort of first kind of picture worry, at least where we have the variable itself should be feeding back or something.
Yeah. Okay. Yeah.
It's not sort of directly unphysical in that way.
Right. Yeah. Shinod, you have a question?
Yeah. Yes, Tarun's question kind of rekindled some of my early interest. So I have been looking at computer simulations a couple of years back. So what I was looking for was, so what I looked at was a couple of simulations done by physicists, but they were modeling the movement of certain bacteria, some modes on various viscous fluids. So one of the things I noticed was that when they describe their simulation model in their paper, they use a lot of analogical reasoning to establish that their particular model is sufficiently similar to the actual swimming of the particular mode on matter. So in the paper you distributed, you also, I think somewhere you mentioned that this representational aspect is also kind of important, but sometimes at least people would argue that this is sufficiently representational of the target phenomenon. So how strong, how often people use this kind of analogical way of reasoning out and saying that, okay, the simulation or the representation model in the simulation is kind of sufficiently similar to that of the target phenomenon, and especially given that in climate modeling it is much more complex with different parts of model with various assumptions. So this also goes back to Professor Jetley's work. So I disagree with him, but that COVID modeling, where one of the issues was that there are a lot of assumptions taking place in the sub models. Then we come out with this. So, with your field study, so can you say something about this kind of analogical kind of reasoning going within, not within, but once they try to explain their model to the readers in the paper, they usually go for this. So have you noticed something like this in the climate model cases?
Let me just ask one question of clarification. When you say analogical reasoning, do you mean like literally saying what we see happening here is analogous to, it's an analogy with, or do you mean that they're saying that it looks similar enough in certain respects to treat it as a kind of, similar enough to the real thing?
Yeah, only the second one, not the literally analogous. The second one.
Good. Yeah, good. So I think then that, yeah, I mean, I think if you want to make the case that what you're observing in your simulations should be understood as something that, like, if you want to make the case that, you know, the how actually explanation of what's happening can be unfolded by reference to what you're seeing in your simulation, then yes, you have a huge amount of hard work to do to make the case that the important elements that you need to have represented sufficiently well how are in fact represented sufficiently well. So that's still consistent with having a model that is idealized and simplified in various ways, but insofar as like certain processes are figuring importantly in the explanation that you're giving, you're going to need to give some account of how whatever idealizations and simplifications have been made, it's not so much that it should lead us to think that we are, inaccurately representing that the inaccuracies are so much that we should not believe in the explanation that we're extracting. So I think this question about, so I had been being kind of cautious and saying like, there's this value explanatorily in doing these kinds of quantitative consistency checks, but we do ultimately want to go beyond that, and we do ultimately want to say that we can explain what's actually happening, not just we've successfully, quantitatively probed our set of background beliefs, and that is where you get into this whole really hard, activity of model evaluation and really probing the way in which the model represents the pieces that you take to be the most relevant to the explanation you're giving, and then making a case that it can be trusted as giving us the correct kind of account, even if it's not perfect. So you absolutely see that all the time in climate, and I take that to be part and parcel of what model evaluation in this context is about. And so like in the last IPCC report, you find an entire chapter on model evaluation where they're trying to show you for all different elements of the simulations that they've generated, how well do they compare with observations as a starting point for thinking about, how well are we representing different parts of the system here. It's clearly not the whole story, but you definitely see that kind of attention. And it is geared toward this goal of arguing that the model is sufficiently similar in relevant respects to be a reasonable, to be something that we can take seriously as showing us the actual explanation, not just a possible explanation. Yeah.
Okay. Thanks, Shinod. Darshi, you have one more question?
Yeah. Okay. So again, that's just to push this general point. I think that for me, what is important is a little bit of contextualism here, because, and I think you have given lots of case studies and all that. So I would say that we need not apply some univocal criterion for whether models explain or don't explain, whether simulation models explain or don't explain, and then use that to say whether your specific model within climate science are doing that or not. So I think we need to go case by case, and I think climate science in particular, meteorology, would be very poor without simulation models. Okay. So I think so they may have more value within certain sciences than they do in other sciences. And in climate sciences, I think it would be extremely poor if there were no, if the simulation models were taken not as explanatory. Again, general.
And I think it partly has to do with, which models we mean. And yeah. I agree with you. I mean, I think, these models that I've been talking about and the sort of complex climate models, they really are intended to make an attempt at representing with theoretical physical knowledge, the processes that are at work. They are intended to be representative, as best as can be achieved. They are not, they attempt to take that kind of realist approach, right? They attempt to be like realist in their approach. They are limited by the fact that, we have only so much computing power and we don't know everything about the system, but that is definitely the mode of operation, as opposed to something like an econometric type situation where you're just estimating coefficients on an equation that you hope will fit data. And I don't mean that to impugn all of econometrics, just a certain kind of modeling that is meant to, fit observations by tuning coefficients. It's not that kind of enterprise in climate science. Not with these models anyway.
Okay, any final questions? All right, I think that's it, and we're also virtually out of time. So I think we'll call an end to the talk here. Thank you so much, Wendy. That was a wonderful talk and really, I think, productive question and answer session. So thanks a lot for being with us today and taking the time to give us this talk. We really appreciate it.
Thank you so much for having me, and to all the people who stuck around to listen and to ask questions. I really appreciate it, and it's actually very helpful for me as well to think about what do I really want to say about all this. So thank you.
Yeah, and thanks also to everyone who participated in the discussion. Please join us next week when we will have Abhishek Kashyap, who is in the chat right now, giving a talk. I hope to see all of you there next week. Thanks, everyone, and good night or good morning. Good night to everyone who is in this part of the world. But see you all next week. Thanks a lot.
Okay.
Bye, everyone. Thank you.
Thank you.